Today we will start to do problems on chapter 14, and then I will introduce for you some calculations related to flat rolling. Okay, and then next time we do problems on them. So just let me open the problems. Do you see the problems PDF?
Not yet.
Yeah. Let me know, please, when you see it.
Yes, فتح دكتور.
Okay. So to start with, stainless steel has a flow curve with strength coefficient of 1200 megapascal and strain hardening exponent of 0.4. A tensile test specimen with gauge length 100 millimeter stretched to a length of 145 millimeters. Determine the flow stress and average flow stress that the metal experience at this strength. So here, in this problem, they gave us the value of the strength coefficient K and the strain hardening exponent N. And we know that when having K and N, we can say that sigma is equal to K times epsilon to the power N. Okay. Now, a tensile test specimen with gauge length of 100 millimeter is stretched to a length of 145 millimeters. So this is L0, and this is L at the final state we reached. Okay. So at this state, we can say that the corresponding value of epsilon is calculated as ln of L over L0. And since we have the values of K and N, replacing epsilon in this equation here, replacing epsilon, N and K in their values, I can get the value of sigma. So when they talk about the flow stress, okay, the flow stress corresponds to the value of sigma at a certain point. So this value will give me the flow stress. Now, if I want to find the average stress experienced at this strain, so when they talk about average stress, it means that we take it into account from start of yield. Okay. Now you know that yield start at a very small epsilon. Epsilon when yield start is very small. This is why we can consider that for the strain hardening flow curve, if we want to find the average value, we can consider that for this point, epsilon is very close to zero. Okay, so epsilon at this point, which is correspond to yield, is nearly zero, and this is epsilon at the point we reached at a certain point. If I want to find the average flow stress, y average, I can do it by integrating this function. Okay, so to find average value of f, I can write it as integral of k epsilon n over delta. So this is the value of sigma. If I want to find an average value for it, okay, I can integrate over this value. So integral k epsilon d epsilon, and I divide by delta epsilon divided by delta epsilon. So what I will obtain when I perform this integration, integral of k epsilon n is equal to k epsilon n plus 1 over n plus 1, and delta epsilon is epsilon because epsilon minus 0. If I consider that epsilon at yield is nearly very close to 0, so it's n plus 1 times epsilon. If you simplify epsilon, you get here epsilon n plus 1 over epsilon is epsilon to the power n. This is why the average flow stress is computed as k epsilon n over n plus 1. Okay, so here all we have to do is to have numerical application of this. So first I get the value of epsilon, which is ln L over L0. The value of flow stress will be k epsilon to the power n at this point, and the average flow stress is k epsilon n over n plus 1. Another problem, a tensile test is performed to determine the strength constant C and strain rate sensitivity exponent M for a certain method. The temperature at which the test is performed is 500 degrees. At a strain rate of 12 per second, the stress is measured at 160 megapascal. And at a strain rate of 250 per second, the stress is measured as 300 megapascal. The first question is to determine the values of C and M, which are the exponents in strain rate sensitivity equation. So you know that in the course material, we have seen that we can develop a relation between the relation of stress and strain rate. Okay, and the form of this relation is similar to the strain hardening relation, which is sigma equal to a constant C times epsilon dot, which is the rate of variation of the strain, okay, over to the power m. Now, for a fixed temperature, so if you are working at constant temperature, we have constant values for C and M. And we have seen in the course material that for low temperature, the sensitivity to strain is reduced because M will be nearly equal to 0. But as temperature with increase of temperature, the sensitivity to strain rate will increase. This is why with temperature, M will increase and C will decrease. Okay? Why we expect that C will decrease? Because we know that when we heat, it will be easier to deform. But also when we heat, the strain rate will affect more the variation of sigma. Now, to start with, for its fixed temperature of 500, we want to find what are the values of C and M. This is why it's like the calculation of strain hardening exponent, and the strength coefficient. It's the same method. I put two equations with two unknowns. All I have to do is to replace by coordinates of the 2 points. So the first point I have has a strain rate 12 per second and as sigma 160 megapascal. So the first equation I can write is that 160 is equal to the value of C is to be calculated. So it's C times the rate, strain rate is 12 per second. So it's times 12 to the power m. This is equation number 1. Equation number 2, I can get it from the second point. So for the second point, I have a strain rate of 250 and a stress of 300 megapascal. So 300 equals to C times 250 to the power n. So this is equation number 2. Okay. And now all I have to do to calculate C and M. So first, for example, to calculate C, I can divide equation 2 by equation 1. C will be eliminated, and I transform it to linear equation. I get the value of M. Then I replace in one of the two equations. I get the value of C. Okay. So this is how I can find the two unknowns C and M. Now, once I calculate them, they are saying if the temperature is increased to 600 degrees, what changes would you expect in the values of C and M? So what we should say is that with increase of temperature, we have increased
M should
increase.
increase.
To strain rate. This is why M will increase. But since with temperature it will be easier to deform, C will decrease. Okay. Any question on this problem? So here I will show you how they perform the calculation. So here first they wrote the two equations. You have several methods to solve for the system. One method is to linearize the system by doing ln for the two equations. And then you will get two equations with two unknowns, M and C. So first they got M. Now when you perform ln operation, sometimes the accuracy of solution will not be very accurate. If you replace M in the first equation and in the second, you might obtain little bit difference for the two C values, but it is fine. Okay, here, for example, to be more accurate, they calculated C from the 2 points and they got the average value. But already they are close, and no need to do this. You can just, as you are used to do, to solve first for M, then find C from one of the 2 points. Okay. And as we said, if temperature is increased to 600, the strength constant would decrease and the strain rate sensitivity will increase. Another problem, a work part, as you can see for chapter 14, you don't have a lot of formulas. Anyway, you have already a formula sheet posted on Blackboard. This formula sheet will summarize for you the main formulas. I will go with the formulas with you for chapter 14 and 15, okay? Because we will start today a calculation part related to chapter 15. Now, a work part with starting height of 100 millimeter and diameter of 55 millimeter is compressed to a final height of 50 millimeters. During the deformation, the relative speed of the two plates compressing the part is 200 millimeter per second. Determine the strain rate at a height of 100 millimeter, 75 millimeter, and 51 millimeter. First, by definition, how you calculate the strain rate? The strain rate epsilon dot for a certain part is equal to the, if you want, the approaching velocity of the tool. So here, the plates that are compressing the part are moving at a velocity of 200 millimeter per second. By definition, epsilon is V, okay, over the depth of the work part we are working on. So over the height here, okay? So here, since velocity is in millimeter per second, then we will use H also in millimeter. So the length unit will be simplified, and then we will get the strain rate in seconds. So you can say that with constant velocity, what will happen for strain with time? So if you have a compression test, okay, if you fix the velocity, as you are compressing, the height is reduced. And what will happen to the strain rate then? With reduction of height, the strain rate will increase. Okay, so here it's just a numerical application. You will see that when calculating strain rate for different heights, you will observe an increase in strain rate with reduction in height. So here we can see the values. As expected, as the height decreases, the strain rate will increase from 2 to 2.66 to 3.9 to 2 second minus. Okay? Any question on this problem? Okay.
دكتور فيك بس تقولي الفورمولا شو كانت تبع السترين ريت؟
Yes. الفورمولا تبع السترين ريت هي epsilon equals to the velocity of the tool used for deformation over the يعني انت مثلا here you are compressing مظبوط. You have this is your part.
Yes, فهمت.
This is your
فهمت
plate.
عليك بس I just wanted to write it down.
Okay, it's V
No
over
need to
H.
repeat.
V over H. So here the velocity direction is like this. So due to velocity, you are reducing height. So you will take into consideration it's V over the depth of your part, the height of your part. Okay?
Okay, thank you.
Well, now what we will do, we will start with formulas on chapter 15. And we will do a first part of chapter 15, which is the calculation part together. And the second part, which will be description of in details of rolling, forging, and extrusion, and wire and bar drawing, will be posted as PowerPoint, recorded PowerPoint. So in chapter 14, we have introduced, if you want, these different mechanisms, but we didn't go into their detail. Okay. In chapter 15, we will go in detail and what are the different types of rolling, what are the different types of forging, what are the machines that are used, etc. But now, as a start of chapter 15, we have a part that is for problems. We will start it. We will start with it together. I will define for you the equations that will be used. Okay, and then I will post the description part as PowerPoint. So this part that you will deal with is concerned with flat rolling. You have already seen what is flat rolling in chapter 14, the description of it. This is one of the easiest types of rolling. So it consists on a flat plate for which we are trying to reduce the thickness using two rolls. Okay. So this is the figure to remind you of the mechanism. This is the figure of the process. So as you can see, you have a flat plate of initial thickness, T0, and your purpose is to reduce this thickness by letting this plate go through two rolls, sorry. The two rolls are moving at the opposite velocity direction. So this roll is moving in an angular velocity in the counterclockwise direction, while the bottom roll is moving in a clockwise angular velocity direction. So, but in this way, it's true that their angular velocities are opposite, but their linear velocity at contact point will be the same. So here, if you take this contact point, for example, the linear velocity will be like this. And also for this linear point, for this contact point, you will have the velocity like this. So this will help if you want into drawing the plate between the rollers. Okay. And in order to have a motion, an overall motion of the plate in this direction, then this velocity, as you will see, will add to V0. So the final velocity will be equal to V0 plus the rolling velocity of the rolls on the plate, which will try to take it in this direction. Okay, so it will add to its velocity, and by adding to its velocity, so V final is higher than V0. What will happen is that the flow rate of material is constant, because we know that when you have a flow of material, it's a constant flow rate here. It's a steady application. So we will see how we will relate the thickness, velocity, and width to, in the initial state, to the ones in the final state using the principle of conservation of mass. Okay, so let us go now into detail. So first, a flat rolling, as illustrated in the figures, it involves the rolling of slabs, strips, sheets, and plates, which are work part of rectangular cross-section in which the width is greater than the thickness. In flat rolling, the work is squeezed between two rolls so that its thickness is reduced by a certain amount. The amount of reduction of thickness is called the draft. Okay, so when they tell you the draft is equal, for example, to 3 millimeters, this means that the difference between the initial and final thickness is 3 millimeters. Okay. Now, concerning D, then it's the draft. T0 is the starting thickness of your material. TF is the final thickness. And sometimes we can express also the draft as the terms of fraction of the starting thickness. This is called the reduction ratio. So the reduction ratio is just D over T0. Now, when a series of rolling operations are used, reduction is taken as the sum of the draft divided by the original thickness. Okay, so we will see together that sometimes we need more than one pass to achieve the desired reduction. Okay, so in this case, if you want, the total draft will be calculated as the draft per pass times the number of pass. So in total, the reduction will be summation of draft per pass times the number, by considering the summation over the number of pass over the initial thickness T0. Now, using the property of mass conservation, we will see that we will relate the input to output characteristics. Okay, so in addition to thickness reduction, rolling usually will increase the work width. So thickness will be reduced, the work width will be increased, and the velocity of motion also will be increased. So these variables, parameters can be related through the conservation of mass. So from conservation of mass, the volume of metal exiting the rolls will be equal to the volume of metals which are entering the rolls. This is why we have that the volume entering is T0 omega 0 L0, where T is the thickness, W is the width, and L is the length if you want. And we have at the final state T final, omega final, L final. Now, to make this equation a rate equation, we divided with respect to time. Okay, so we have that W0 and WF are the width of the plate before and after moving through the rolls. L0 and LF are the length before and after. And in this way, if we divide by the time, okay, so if we derive this relation with respect to time, then the derivative dL by dt represents the velocity of the metal when passing. Okay, so before passing through the rolls, the velocity was v0. The velocity after passing through the rolls is v final vf. So by the derivative of this relation will allow us to relate the initial and final velocity through this relation, which is this is due to conservation of volumetric flow rate. So if you want, this is conservation of the volumetric flow rate. Okay, and we will use it to relate inlet and outlet velocities from the two rolls. Now, the rolls contact the work along an arc defined by the angle theta. Each roll has radius r, and its rotational speed gives it a surface velocity vr. This is the linear velocity. This velocity is greater than the entering speed of the work v0 and less than its exiting speed. Why we have this condition? Because to be able to, for the plate to pass the rolls, I should have this condition. So V0 before is smaller than Vf. This will lead smaller than Vr. So the Vr will contribute to an increase in velocity of the work to move through the rolls. And in order to pass the rolls, the final velocity Vf will be higher than Vr. Since the metal flow is continuous, there is a gradual change in velocity of the work between the rolls. So this increase will be gradual from V0 to Vr. However, there is a point along the arc where work velocity equals to the roll velocity. This is called the no-slip point, also known as the neutral point. So when moving from V0 to Vf, you will pass by a certain point characterized by Vr. This is called no-slip point. No slipping means that we don't have relative motion between the tool and the work. Okay? On either side of this point, slipping and friction occur between roll and work. The amount of slip between the rolls and the work can be measured by means of the forward slip, a term used in rolling that is defined by. So the forward slip that will lead to movement of the work to pass through the rolls is calculated as the difference between V final minus V rolls over V rolls. Where S is called the forward slip, it's without unit. Vf is the final exiting work velocity, and Vr is the roll speed, linear speed in meter per second. So if we look at the figure here, so in this figure you can see the linear velocity is calculated here as the angular velocity times the radius. Okay? So you have a certain value for your linear velocity. Now what will happen is that when entering through the rollers, the velocity is smaller than Vr. Then Vr will push the work to pass through the rolls, okay, leading to increase in its velocity. And at a certain point, due to this increase, first, for example, at this level, the velocity was V0. When passing through the roll, this velocity will start to increase gradually. It will increase at a certain point, it will reach the value Vr. So the contact point in this case, so let's say here, for example, at this level, we can say that I have a neutral point where the velocity of the work will be equal to the velocity of the roller. Okay, and after this point, I will have velocity of the work part higher than velocity of the roller, so which will contribute to forward motion, and the final velocity will be Vf. Okay. Now, what will happen is that in general, whenever you have, at this point, I will not have slipping. At all other points, I will have slipping between the work and the roller. Okay, this means that, for example, when I was here at a certain point here, the friction force of the roller on my work part was in this way, because the friction, okay, is opposite, if you want, to the relative velocity. So here, since the velocity of this roller was higher, then this roller will push the work part in this direction. After this part, when the velocity of the work part will become higher than the velocity of the roller, the friction direction will be opposite. But the net force, when you compute the net force on the work part by integration, the net force will be in this direction. So you will design it in a way to have a net force to push your plate to go out of the rollers. Okay? So here, going back to the given. So in case of rolling operation, the true strain experienced by the work in rolling is based on before and after stock thickness. And the equation, because it's compression, okay, epsilon is given by an absolute value. It's ln T0 over Tf, T initial over T final, okay? Because this is, we are squeezing the part, so the thickness is reduced. Now, the true strain can be used to determine the average flow stress applied to the work material in flat rolling. And the value of the average flow stress is calculated by K epsilon n over 1 plus n. So this is the average force experienced by the area in contact with the roller. The average flow stress is used to compute the and estimate the force and power in rolling. We will see how. Friction in rolling occurs with a certain coefficient of friction, and the compression force of the rolls multiplied by this coefficient of friction will result in a friction force between the rolls and the wheel. On the entrance side of the no slip point, friction force is in one direction, and on the other side, it is in the opposite direction. This is what we talked about. However, the two forces are not equal. The friction force on the entrance side is greater, so that the net force pulls the work through the roll. If this were not the case, rolling would not be possible. There is a limit to the maximum possible draft that can be accomplished in flat rolling with a given coefficient of friction, which is defined by the maximum possible draft is the friction coefficient square times the radius of the rotor. Now, if I want to just do the analysis of these terms, okay, the average flow stress is applied on the contact area between the work part and the roll part. So this is the contact area. Here I have a certain arc of circle, and I have the length of my, of course, I have a certain length of my work part. So the contact area will be equal to the length of my work part, or the width if you want, the width, times this arc of circle, okay? And by calculating the average stress, the stress is perpendicular to this part. When I calculate the average stress, I can multiply the average stress by the area to get the total force applied. Okay. Now, you know from if you have taken static courses or dynamic courses, you know that if I have a normal force and I have a rough surface, okay, the friction force is related to the normal force by which relation? Who remembers? If you have a surface, okay, and it's a you have a certain normal between the surface and the force. If you want to compute friction, let's say you have motion, for example, in this direction, then friction will be opposing motion. This is V, let's say. This is the friction. F is calculated as mu times N, if you remember. F is equal to mu times the normal. So the friction coefficient is used to calculate the friction by multiplying the normal force between the surface and the object by mu. So the force F between the two, between the friction force between the rollers and the work part is depending on the force, the interactive force between the two and the friction coefficient. So if we don't have friction, it's not possible to accomplish the rolling operation. Now, concerning the relation between draft that is possible and friction, we have developed an empirical relation from experiments. We have seen that the maximum draft that can be performed in one pass, so if I pass my material one time through the rollers, the maximum draft I can reach is the radius of the rollers times the number, the coefficient of friction of the surface between the two surfaces to the power 2. Okay, so without friction, I cannot do any draft. I cannot achieve any draft. Now, given a coefficient of friction sufficient to perform rolling, the roll force required to maintain separation between the two rolls can be computed by integrating the unit roll pressure over the roll work contact area. Okay, so we have seen together that if you have the force, the total force acting between the two, okay, is integral of the pressure times dA. dA is the elementary area. The elementary area is dl, which is the small thickness of the arc of circle, times the width. Okay, so here if I perform my integration, I will see that I can use the average flow stress instead of doing the integration, because integration requires knowing the variation of pressure with location. So an easier way for computation of the force is by considering the average stress value times the contact area. So as you can see here, an approximation of the integration can be calculated based on the average flow stress experienced by the work material in the roll gap. And this average stress is given by the average force. It's given by the average stress times the area of application. The area of application is the width of the work part times the length. L here is the contact length between the rollers and the work part. And we have a certain relation that will give us an approximation of L, function of the radius of the rollers and the initial and final thickness. So it was shown that the contact lengths can be approximated by radical R times T0 minus Tf. If I go back to my figure, this is L. L is the contact length between the rollers and the work part. If I multiply it by the width of my rollers, if you want, it will give me here I should multiply it by the contact width. عادة بيكون ال width of the rollers أكبر من width of the part. So I should multiply it by just the width of the part. So it's width of the part times the length of contact. Okay. And as we have seen, L can be computed function